All right, so we're gonna talk about the properties of conjugated diene. Start with the bond length. So I'm comparing between a bond length between C2 and C3 of a conjugated diene on the left side and a regular hydrocarbon on the right side. Okay, you can see that this bond length between C2 and C3 is shorter, and the reason is this bond length is made from two sp2 carbons versus a regular alkane. This bond length is in between two sp3 carbons. If you still remember the hybridization theory, an s orbital have characteristic of short and fat, p is long and thin. The mixture between s and p have some characteristic between p and s. Okay, give you some example. If you mix them 50-50, so the length gonna be longer than an s orbital itself, but still shorter than a p. If you add more p, so in sp2, right now we have, if you do the math, so 33% s, 70, no 70, 16, 66% p. You do the math right there. So it's gonna be, this one gonna be longer than sp, and sp3 add more p into it, so this guy gonna be look more a lot more like p orbitals. So going to be the even longer. Okay, basically my point is an sp2 can form a bond but shorter than an sp3 carbon. All right, and you can read down here as well. Anywho, so that's bond length. Now move on to the stability of alkenes. Just to review, so normally if a chemist want to know if a compound is stable or unstable, relative stability, so they usually do reaction and measure the heat, either heat in or heat out. Okay, and alkene normally, so they do hydrogenation or they do combustion, either way. So let's say we do hydrogenation. What happens? So you get an alkane, and this is an exothermic process. Okay, I'll start with the word exothermic process. So you guys know it's release energy, but why though? Well, the starting material contain a pi bond and a sigma bond. Okay, the product contain two sigma bond, and sigma bond is more stable than the pi bond. That's why this process it releases energy. All right. All right. Now we're gonna measure the relative stability of a conjugated diene compared to just a regular alkene. All right. So at the top we have conjugated diene. At the bottom we have just isolated or regular alkene. So at the top we got two double bonds. We do hydrogenation, produce some amount of heat. At the bottom only one single bond. But if we do two of them, we should expect that this heat should be the same energy, should be the same amount. All right. We found out that actually that's not really true. The conjugated diene produce 15 kilojoule less than a regular 2 moles of regular alkene, and that's we call the stabilization energy because it's more stable. Right? Anything that have conjugation is more stable, so it releases less energy. We move on to the next chapter. We have the not just diene, but it's just a conjugated pi system, multiple double bonds, and these guys are much more stable than a conjugated diene. Okay, we will get there on the next chapter. All right, before we go, so just a practice real quick. Which compound produces the most heat upon catalytic hydrogenation with palladium metal? So if you do reaction on all three of these compounds, all of them are dienes, which one produces the largest amount? Which means that the most unstable. All right, and that's going to be, the allene. Yeah, so this guy is the most unstable compound, right? So A going to be like produce the most energy. If I ask you to rank, you should be able to do so. A, now go to C, so two alkene. This is the isolated alkene, and then the B going to be this guy. B is the conjugated diene, so they produce the least or amount of energy. Okay. All right. Let's move on to the next one.